All right, let's get started. Yeah, we didn't have a Diva Warn meeting this week. We had a pretty nice open source meeting yesterday. We had presentations by our GSOC scholars, and then we had a discussion of this event that Active Inference put on Wednesday, and that was the review of the paper, The Value of Open Source. And I mentioned that because I was one of the people in the discussion. So, there's a lot of really interesting discussion about this economic model of open source's value, economic value, and then, considering why, what the market looked like and everything else, kind of from a business perspective. So it didn't really consider a lot of motivations or, there's some talk of innovations, and we kind of spooled out that discussion of innovations. So, like, for example, if you say, for example, create an operating system by virtue of there being an opportunity to do something in your community, like, for example, if you build something like NeuroFedora, you have tools that you're building on, but you're also building something new for other people. And that's an economic benefit to your community. So, and then of course the maintenance part is also an economic benefit if you invest in maintenance versus not, and it persists and sustains those works. So it's a really interesting discussion. Yeah. So, and then Jesse had a discussion on, I don't know if he'll be here today, but a discussion on being a project leader, and he was teasing what he was going to present today. So we'll see when he comes in. We'll slot him in somewhere. So Morgan, did you have some things to update us on,
or? Yeah. So really great meeting up at the Allen Institute on open science in undergraduate education. It was a group of, mostly biology professors. Although I was happy that neurobiology was strongly represented. And so some great keynotes. It was a group of, like, or the keynotes were like, some people who literally work on, theory of education,
right?
And that are, kind of like doing A/B testing of curriculum.
Right.
Right. But also some professors and one in particular is just, you could just tell that this is one of those super lecturers, like she just knows how to, she's a microbiologist, and a lot of her stories were about poop. but she made it all relevant.
Right.
Yeah. So, and like her particular initiative is connecting science to civics. Right. So, yeah, like really inspiring. And then, much like the meeting with Protocol Labs Neuro, where it's just like, there was also a roundtable on current funding issues, and which was like, just sad,
Yeah.
you know, to just hear all these people struggling and hear them, you know, not struggling, but just like especially early career people who were just like, well, what am I supposed to do now?
Yeah.
You know, and yeah, but really great. Super glad I went. There's that San Diego professor Ashley Jevnet. I can't remember how to pronounce her last name.
Yeah, I think I know who you're talking about.
She teaches like Python programming for science.
Yeah.
I mean, you know, but she's like a neuroscientist by training.
Yeah.
Well, like a neurobiologist by training.
Yeah.
So she takes a lot of Allen Institute examples, and yeah, so it was great because at the same time, like it was a great. There was a bunch of people who I could talk to about like what they thought the role of extracurricular projects were, and you know how useful was basically what NeuroTechX does in terms of student clubs and providing, you know, what our goal is, which is to provide a research opportunities for students that don't have those, you know, or you know haven't found a lab that they can work at, or perhaps their institution doesn't have one. Right. And so yeah, it was great. Like really hoping to hear more from Ashley in terms of her engaging with the UC San Diego student club.
Yeah.
And you know, I felt particularly good pointing her at that because they had just, together with the 5 University of California schools, they had just put on a conference.
Yeah.
Like a student-run conference.
Right.
And in San Diego. So anyway, like I think that's great, and like made lots of connections, lots of people at liberal arts schools who've got motivated students, but don't have the kind of the research groups to connect them to, at least at their local institution, and yeah, as well as just like getting the opportunity to hear your teachers talking amongst themselves about best practices and sort of like how the sausage is made of undergraduate lectures.
Yeah.
So and like what resources do they have to draw on, which was also a big part of that. BioQuest was a big BioQuest was one of the or somebody from BioQuest was one of the keynotes.
What's BioQuest?
It's like a, imagine an educational foundation nonprofit that works to collect and disseminate educational materials,
Okay. Yeah.
and it's like trying to be sort of a repository for people to share, and as well as develop. So that was great, and then we got the news. So I mean, I was also representing Biopunk Lab, in terms of like to some degree, biotech was more relevant. also got to meet the student groups there, like people from UW, being local Seattle. Students from UW were there too, and that was interesting in terms of science communication. And so I hope to link them together with NeuroTechX as well. We also at a kind of combined biopunk NeuroTechX thing, we applied for a workshop at, excuse me, applied for a workshop, 3D bioprinting workshop at Carnegie Mellon this summer. So that'll be in mid-July. And it's really, really exciting. Yeah. Great group that is definitely pushing bioprinting. Their research, it seems to focus more around like trying to print a human heart. But I like that that's at least that's also bioelectric. and I think so at least one of my teammates, I can bring two people in addition to myself. So one's who's already joined and is a part of our neurotech floor at the Frontier Tower. So he's a 3D printing guy from NASA who works on kind of like, more solid kind of 3D printing. Yeah. But he's an expert of that and is already familiar with CMU's next manufacturing group. Trying to think about who else would be appropriate, but like our goal to, the NASA guy's goal too, is really like extending that mind in vitro kind of project that is at UIUC. Yeah. And it's yeah. I mean, I'm really happy to have James, who's can understand the kinds of lithography that's being used to fabricate the microelectrode arrays on these things. Yeah. So he understands this kind of metal work, like this kind of nanofabrication metal work. But then, so it's like, it's a combination of that 3D printed parts and then open EFIDs, right? And so that you can, build something that's comparable to a commercial MEA, right? And this is the one piece that's missing from the Braingineers kind of open hardware lab automation, lab tools for organoid culture. So I'm still thinking about like what other kind of expert would be appropriate to kind of take this project to the next level. In terms of like thinking a little bit about some people who there's some people reaching out to that make artificial skin, just because they skin is an easier one to think about, basically layers. Yeah. And then the artificial skin people then care about kind of like the physics properties. They're kind of like mechanics of what you've bioprinted, or do we just lean into the kind of the neural? But really exciting. Like, so we're we're using the few remaining weeks to think about how we can show up at Carnegie Mellon and not only do this workshop where you basically, part of the cost is like you build the 3D bioprinter and then you get to take it home.
Okay.
So the cool thing is, like, we're going to be able to bring this back to the lab, right?
Yeah.
The question we have is, like, are there any other connections and any other kind of technologies where we know we're trying to build this kind of, neural recording device? What else can we add to it, and what other kind of connections would be appropriate?
Right.
But super excited about that, and we're writing that up, and we'll have a presentation on that for sure, because we're gonna be presenting in July. And then this weekend, what's exciting on Monday is that Kernel is coming to the tower. And Kernel is this neuroimaging company. Did I mention this already?
No, I don't think so.
Okay. So Kernel's is, kernel.com, co. This is a Brian Johnson funded neuroimaging device. Okay. It is a whole head near infrared spectroscopy system. They've made custom ASICs to like having deep pockets allowed them to develop a certain amount of fabrication, like electronics device manufacturing, such to really reduce the cost and have this like very high density array, a multiplexed array of emitters and detectors. So it's like 1,000 channels, in a helmet.
Yeah.
And it's a very, it has limitations that near infrared spectroscopy has, in the sense that like it's only so deep into the brain.
Yeah.
But in this case, it is whole head coverage, So trying to think about, we get the device for a couple months. We're working with them on brain age prediction and some other measures that they're kind of beta testing. I'm going to be reaching out to San Francisco researchers and seeing if anybody else wants to kind of try collecting some pilot data and see how useful it is. But it's exciting. I mean, it's exciting to have a real real brain imaging device at the tower, and at least for now, not have it just be EEG.
Yeah.
So yeah, that's great, and it's nice that he's coming up to give a talk as well. We've got an event going on for the next 6 weeks that's kind of AI and longevity focused. Okay. So their brain age prediction measures is super relevant. So that's very nice of Ryan Fields to do this.
Yeah, that's great. So keep up the good work, I guess.
That's cool.
Yeah, it looks like things are kind of floating on a number of fronts.
Yeah, and I see human brain mapping events started.
Okay.
So like pre-conference workshops, like NeuroDesk. Stephen Bowman's based in Australia, where it's happening. I mean, it's happening in Brisbane.
Oh, okay.
I know he's already doing a NeuroDesk workshop.
Oh yeah.
Yeah.
What's the link for the conference?
I'll find that. That'd be easy. Let me since I just on this. I'll give you a link for the 3D print workshop.
What's the 3D print workshop?
And I don't know if this is the best link. I'll try and see if I can find something a bit better in terms of covers more of the kind of workshops and things.
Right.
And here's a picture of the kernel device. Yep.
Oh yeah, I've seen that before.
Yeah.
Right.
And Michael Levin just posted the next chapter. What does it say? Next chapter, the saga of the Anthrobots is out in final form.
Oh, okay. Well, which one is that?
And I'll also get a link.
So yeah, this is the Human Brain Mapping Workshop, Organization for Human Brain Mapping, OHBM. Yeah, so this is happening in Brisbane, I guess, this next week. So looks like it's coming together. Their featured speakers, symposia, the workshops. I think we talked about that with Stefan Bullman, and then yeah, I don't know if they have a link. Okay, so let's go over the featured speakers. So what are they interested in? Paul Thompson is talking about worldwide collaboration of artificial intelligence in the global quest to map human brain diseases. AI and brain disease thing. Yeah.
Yeah, so he runs the Enigma Consortium.
Yeah, the new Enigma toolbox.
Which is the, it's kind of like the last neuroimaging work that I'm still involved with.
Okay.
He just posted a video covering his here I'll find that too.
Okay.
And just drop it in the chat. But yeah, it's not necessarily his keynote, but okay. Now it is hard to search for Paul Thompson.
Yeah, because there's somebody.
I'll find a link.
All right. So yeah, this is about Enigma. This is the link to the project. Adil Razi is talking about mechanisms of mind, regenerative brain models, and psychedelic neuroscience. So more about neuroimaging and then generative modeling. So that's a very similar kind of thrust. Melanie Boley, consciousness from theory to practice. So some things in consciousness and the IIT, which is the integrated information theory approach to consciousness, and kind of talking about that. Joanna Cabral is talking about the network illusion and functional brain mapping. So this is, I guess, thinking about functional networks, functional connectivity, and networks. And okay, so this is let's read through this one. This sounds interesting. This keynote examines our tendency to interpret correlated brain activity as evidence of neuronal interactions. While functional networks have become a cornerstone of modern neuroscience, this talk explores whether long-range correlations of brain activity necessarily reflect the propagation of information through axonal connections. So you could have alternative explanations for these correlated patterns, including principles from wave physics, biomechanics, and fluid dynamics, which may drive similar macro-scale dynamics not yet relying on axonal pathways. By reconsidering the nature of functional networks, we can develop models that better explain how these activity patterns support healthy cognition and how their disruption may lead to cognitive impairments and psychiatric symptoms. So this sort of complements rather than discounts a lot of the functional connectivity research. But I think it's interesting that kind of adding maybe another layer onto the network approach and how the network approach is typically applied to the brain and how we understand these kind of connections between our units in a network. Alessandro Gozzi talking about mechanisms of functional disconnectivity. So this is where we have disconnectivity, which is, of course, dysfunctional communication amongst brain regions. And then what are the biological mechanisms of that? So talking about cross-species research, getting at some of the molecular and neurophysiological underpinnings. And yeah, really taking that cross-species approach. Anki Q, fetal programming and maternal psychological stress. So this is a talk on brain development and mental health. This is Lucina Udin, towards a universal taxonomy of functional brain networks. So this is on sort of, thinking about different networks, functional networks, and thinking about how to classify them, what they're doing, what are the core aspects of functional networks, and what are their spatial topographies. So this is this project .NET.
Yeah, I was just going to say, she just had a really interesting kind of review article on resting state fMRI.
Okay.
And kind of like its history, and I forget what its history and its future or something like that.
Yeah.
Just really, everybody's been talking about it on social media.
Okay.
Yeah.
Okay. And so there's also this network correspondence toolbox that permits researchers to examine and report spatial correspondence between novel neuroimaging results of any one group doing experiments, and then multiple widely used functional brain atlases. So that's nice. Sharna Jadamar is talking about glucodynamics in the metabolic network of the human brain. So this is about glucose signaling and being able to uncover the metabolic aspects of brain activity. So they're using PET and MR data and kind of thinking about the metabolic network and making insights. Okay. So those are the speakers there. Again, like Morgan said, a number of workshops, including on some of the projects that Stefan Bowman is involved in. Okay, so yeah, we have a couple things in the chat. We have, go ahead.
Yeah, I was going to say, I put one link there. They are hosting a tour of the Australian organoid facility. like there's specifically a brain organoids tour going on as a part of human brain mapping.
Yeah.
So I just wanted to point that out.
Great. Yeah, it looks good. This is they have a little poster here where they talk about what organoids are useful for and how you get organoids and all that.
It's not too surprising. So Adil Razi is science officer, or like science advisor to Cortical Labs.
Yeah.
Like they're, and because he's a local, I'm sure he's also involved in the organizing committee.
Yeah.
Anyway.
Organizing organoids, yes.
I was happy to see that organoids were prominently represented.
Okay, yeah, that's good. Yeah. How much it's OHBM, so they're doing a lot of stuff with organoids, or is this like an up and coming area?
No, it won't be. It's OHBM, so it's basically it's basically MR people,
Yeah,
like
humans.
brain researchers who use MRI.
Yeah.
With another tier of kind of like EEG, MEG, PET, not so much. I mean, like it makes sense to use PET for something like metabolism.
Right.
You know, but yeah, a lot of structural MRI and a lot of functional.
Okay. This is the morphological, behavioral,
Yeah.
and transcriptomic life cycle of Anthrobots. So this is the Michael Levin, Leo Pio Lopez paper, and this is on the Anthrobot stuff. So what did you want to say about this?
Well, I mean, so it literally popped up as a notification while you're
Okay, yeah.
talking.
Well, I saw the preprint of this. So
okay.
This is, we didn't talk about it yet, so that's why.
Yeah. I mean, it's in the back of my head. I mean, the 3D bioprinting is super awesome, and because we were already looking at this kind of like MEA device, that seemed really cool. In the back of my head, I'm still thinking about this work, right?
Okay. Yeah.
In the sense that like, how do we, how accessible is this, right?
Yeah.
It's super remarkable, like from a microscopy standpoint, it doesn't have to be super advanced, right? It's you're not you're not really kind of making. I mean, this seems like more molecular than previous papers, right?
Yeah.
There's a certain amount of just micro manipulation of cells and of small objects that seem to be the kind of technical challenge.
Yeah.
And I forget what I forget what he said his postdoc or the person who had kind of done most of the work
Yeah.
was like a micro manipulation expert.
Okay.
Like I forget what those skills came from.
Oh,
but
yeah.
but using micro manipulators,
right?
Excuse me, to make a to do these kind of cellular rearrangements, right?
Yeah.
So anyway, it's because what it demonstrate, or it does get at a different. I was trying to explain why organoid intelligence. Like people ask me, do you think you can use organoids to do compute? I'm like, no.
Yeah. It's always the first and last question on that. Like,
but I think that organoid intelligence is a great target.
Right. Because it's not really compute in the conventional sense. It's more like, can it produce a behavior that's intelligent?
Well, it's sort of. I mean, like certainly there's that, right?
Yeah.
In terms of just like you kind of, yeah, you need to redescribe how you're using these words.
Right. Well, yeah.
Right. and but there's also just in the sense of like, organoids as I mean, the things that Alison Vautry studies, the things that Mel Lancaster study, right? They're trying to grow natural tissue types, right? Like what would you get if you grew these tissues?
Yeah.
In an actual brain, right? Organoid intelligence, you can go for non-natural targets, non-natural tissue targets, right? you get to design the way you want the tissue to become.
Yeah.
Towards this goal, right? This, it's for an engineering goal, not a brain science goal.
Yeah.
Right. So that's interesting too, and that's where you get this kind of like alignment towards Levin-like, um, it's not regenerative medicine,
right?
but it gets at this question that Levin brings up, which is like, why can't I choose? Like, I don't want to just grow an arm. I want to grow an arm that has big hands or something like that. Right?
Yeah.
Like I don't know, big hands doesn't, that was all I could think of.
Right.
I think I've got that movie. In my head. With Everything All at Once or whatever.
Okay.
But you see what I mean? Like, I forget what he calls it, the anatomical compiler.
Oh, okay.
Right.
Yeah.
So it's just like if you choose, if you, and in this case, you want something that, you could better I want a tissue type which I can better understand if I've got an electrode interface with it, and I'm trying to stimulate it as a form of communication, signaling, something.
Yeah.
Right?
Yeah. And so in doing so, we bring back a computational concept and confuse it some more. But yeah.
I mean, it's like, obviously Anthrobots goes further and is like self-organizing, but I'm actually okay. I'll find one more article, and if you could actually get me the PDF, that would be awesome.
Okay. Yeah.
But it relates to this in terms of 3D printing, and I'll show you in a second. Yep.
All right. Yeah. So yeah, let's go over this abstract. I wanted to get into this paper eventually. So this is about kind of their Anthrobots work, and they're talking about different aspects of the phenotype of a organoid. So fascinating aspects of morphogenetic and behavioral plasticity of living material are revealed by novel constructs that self-construct from genetically wild-type cells. So they're not doing any sort of inserting of genes into these organoids. They're just kind of like watching them self-assemble from, I don't know, chemical cues perhaps, or whatever's in the medium, whatever kind of scaffolding they're using. And so Anthrobots arise from cultured adult human airway epithelial cells. So they harvest the cells, they culture them, and they put them into this environment where they can build these self-organizing systems. Developing, becoming self-motile, and acquiring neural repair capabilities without exogenous genetic circuits or inorganic scaffolds. So they're actually not using inorganic scaffolds to build these, they're just using the basic environment that you would use for fostering cell culture. Progress in bioengineering and regenerative medicine depends on developing a predictive understanding of collective cell behavior in novel circumstances. So we need to be able to do this. If we want to take some input cells, put them into culture, and we want a certain structure, we should know what kind of conditions to put them in so that we can get them to form that shape. We don't want to have to use all sorts of inorganic materials and sort of guide it, because in a lot of surgical contexts or a lot of contexts in the body, you can't really work with these kind of inorganic scaffolds because the body rejects them. So you have to have you have to kind of know under what conditions you can form these structures without too much guidance. Towards that end, here are a number of life cycle properties of Anthrobots, including their morphogenesis, maturation, and demise, are quantitatively characterized. So their goal is to build some sort of at least predictive model so that you know under what conditions you can form these structures and be able to predict this with a pretty good level of accuracy. A self-healing capacity and remarkable reduction of epigenetic age upon morphogenesis are uncovered. Transcriptomic analysis reveals that assembling into Anthrobots drives a massive remodeling of gene expression relative to their cellular source, including several embryonic patterning genes and a shift towards more evolutionarily ancient gene expression. So this is where the cells are not behaving like something you might find in development. They're actually changing your gene expression basically because they're in a different environment. They're doing other things collectively. So they're sort of impacting each other's gene expression. And if you sample like the Anthrobot versus like an embryo or something like that, you would get a very different transcriptomic profile. And so again, embryonic patterning genes, we might expect those to shift their gene expression. And I find the idea that, you have this more evolutionarily ancient gene expression pattern interesting, but it makes sense because if we think back to the origin of embryos, embryos are basically some sort of multicellularity that isn't quite, there was a point at which you just had this sort of multicellularity, and then you ended up with embryos and more formal multicellular organisms. So very early morphogenesis was kind of like this transitional multicellularity. And in fact, that's what you have here with Anthrobots. You have this sort of transitional or basal multicellularity that is very similar to this, I would assume. These data reveal new aspects of engineered multicellular configurations in which wild-type adult human cells self-assemble into active living constructs with their own distinct transcriptome, morphogenesis, and life history. And then they get into some of the experiments here. This is the cell cultures of the Anthrobots, showing these constructs, showing their, some of the things they're doing with these are called spheroids because they form these spherical structures. And they have data here on the biomass and the growth and things like that. Then they also have some transcriptomic data. So you have this fold change in transcriptomic gene expression. So you have gene expression changes that are negative and positive here. So it's up and down regulated. So genes, usually you compare any number of genes with sort of an internal reference, which are your housekeeping genes, or you compare them with some other system, and then you look at the change, the up and down regulation. And they do this with fold change because that normalizes it. So this is the fold change for Anthrobots. You get this, I guess this is all living organisms and eukaryota. So this is figure 2E and F. For E and F, the x-axis shows the evolutionary ages of ancient genes. Here are all living organisms in eukaryota. The former corresponds to eubacteria, bacteria and their descendants. So that would be all living organisms. And then eukaryota would just be eukaryotes. So the y-axis shows the gene counts here. It's a number of genes. And then, so they give a lot more information in the supplement. But basically, they're looking at Anthrobots and as sort of a function of, or as maybe a constituent of evolution, and how that kind of fits into the evolution of embryos. This is certainly something I'd like to follow up on, but right now I can't really parse too much more out of this. Then they have some other figures here. Yeah, well, we'll have to go through this maybe in more detail in DevoWorm. I think that would be good. Okay, so this other paper here is this is
that's the second one. Do the one above. I mean,
this one. Yeah,
they're somewhat related.
All right, this one.
But it's just this point about again like what are Anthrobots,
right?
Right, and they're to some degree you're you're removing cells from their original, I want to say, multicellular context, right? I mean, it's still in this early stage of development,
right?
So that's important to mention, but it is but it is then about how you've rearranged them, and then how they self-organize after that, right? And like bioprinting is not exactly what they've been doing, but shares overlaps in terms of the problem and the considerations, right? Yeah. And I'm certainly trying to find the right people thinking about this, and in useful ways. And this particular group, Zev Gardner's group, seems to be, yeah. Okay. And yeah, if I can't get further than the abstract so far.
Oh.
So if anybody's able to message me a PDF, that would be great.
Oh, yeah. It's like there's full text here, but I don't know. Maybe I can get to.
No, I can tell you, Cold Spring Harbor seems to be in that tradition of yeah, they're not releasing stuff.
Yeah.
But the second paper to the configurational entropy, again, it's just interesting to think about in terms of how would you do the modeling that, like, to some degree, Josh Bongard's doing.
Yeah.
Like how can you make Josh Bongard's simulations, robotic simulations, which is really Anthrobot simulations, more like James Glazer's, Yeah. And I'd love any other good references and thoughts on that.
Yeah. So this is okay. So yeah, this paper here is 4-dimensional bioprinting. So they want to basically create these living inks, so put cells in like inks and print them out, and then have this. Oh, go ahead.
Well, but different than ink, right? Like it grows. It grows from where you
print it,
deposit.
Right? Yeah.
Right. So you can you can you can put that into the consideration.
Yeah.
Right? Like and that goes not only for where you deposit, but also like how you scaffold.
Right. Yeah.
And is your kind of your media or your scaffolding, encourage a particular anisotropy, for instance.
Yeah.
Mm.
Yeah. I mean, you can do this without 3D printing, but it's not very precise.
Yep.
So yeah, this is where they're doing 3D printing with like these, they're putting things in a medium, they're depositing it somewhere, and you can then control sort of how it's deposited, and then you can go from there as the cells in that medium grow and expand. So,
and this is where it like kind of links in with some of the other topics in regenerative medicine and regeneration. Is that like you can also consider actually electrifying the medium.
Okay.
And that in itself creating a particular directionality and or bias, yeah. Which is another super interesting topic.
Yeah. Okay. So this is where they're talking three-dimensional printing. Now in the title they say four-dimensional bioprinting. So three-dimensional bioprinting is beneficial to tissue engineers because it allows you to rapidly build elaborate 3D structures from cellular material inks. However, predicting changes to the structure and pattern of printed tissues arising from their mechanical activity of constituent cells is technically and conceptually challenging. We've talked a lot about this in DevoWorm, where you have this mechanical integrity that needs to be intact to build structures, and it's not just putting cells in proximity, just throwing them together. They have to sort of grow some sort of extracellular matrix, and then they have to coordinate their activity. So it's not as simple as just shoving them into a gel and then putting them somewhere. They have to establish this sort of mechanical connectivity. And so this perspective is targeted to scientists and engineers interested in 3D bioprinting, but from the point of view of cells and tissues as mechanically active living materials. So you have these dynamic forces to deal with, and it's very hard to deal with when your sort of paradigm for production is largely inorganic materials. So you don't have to consider how the cells interact or how they grow or how they change shape or any of that. This is not, so this is a unique set of conditions that we have to consider. Consideration of self-organization following 3D printing takes the design and execution of bioprinting into the fourth dimension of cellular activity. So that's what they mean by the fourth dimension, is this sort of, post-deposition, or, how do you enable some of the things you want post-deposition? That's the fourth dimension. We therefore propose a framework for dynamic bioprinting that spatio-temporally guides the underlying biology through reconfigurable material interfaces controlled by 3D printers. So that's an interesting article. And then the next paper here is configurational entropy is an intrinsic driver of tissue structural heterogeneity. It's in the same group, and where they talk about measuring tissue heterogeneity with configurational entropy. Again, trying to build that predictive model of collective tissue behavior and trying to control it and understand it at that level. So tissues comprise ordered arrangements of cells that can be surprisingly disordered in their details. And so how do properties of single cells and their microenvironments contribute to this balance between order and disorder? And this is at the tissue scale. So they use a human mammary organoid as a model. They find that organoids behave like a dynamic structural ensemble at that steady state. We apply a maximum entropy formalism to derive the ensemble distribution from three measurable parameters. The first being the degeneracy of structural states, interfacial energy, and tissue activity, which is the energy associated with positional fluctuations. We link these parameters with the molecular and microenvironmental factors that control them to precisely engineer the ensemble across multiple conditions. Our analysis reveals that the entropy associated with structural degeneracy, sets a theoretical limit to tissue order and provides a new insight for tissue engineering, development, and disease progression. So that's again, applying this method. I guess it's I guess it's a nice. They're a nice pairing, and they kind of fit into the Anthrobots area. So taking those three papers together, that would, I don't know, like, I guess this is something that is inspiring to Morgan's work specifically, but I think it's also interesting from the standpoint of thinking about embryos and cell collectives and tissue formation.
Yep. And so really looking forward to this opportunity at the 3D bioprinting workshop.
Yeah.
Yeah. So trying to get up to speed on the latest, and use our time there to try and connect with more of these tissue engineering groups that they're there at CMU.
Okay. So Hussain is here. Well, Hussain.
Hello.
Yeah. Hi.
Hey, how you guys are doing? Good. Yeah.
Oh, pretty good. I see you wrote something in the chat here. Do you guys want to talk about this here?
Just doing some another opportunity onto the Slack channel. Just see. It looks like. All right. So obviously not putting carts before horses, but this is just an idea of okay. So it looks like there's this initiative for the Central Collective Intelligence Project with the Global Dialogues, CIP governance models. So basically, I don't remember exactly where I came across this. Must have been one of my 50 billion Discord servers that I'm part of. All right, so collective intelligence systems pose a lot of problems and threats to society, and this initiative is about developing new models to help the world safely and inclusively guide the technologies like AI, like mixed reality, decentralized platforms for different things, whether it's maybe like a biotech startup that is now being completely autonomous by scientists and robots and things like that. And one of the problems that many models for governing things from either political or political ethical perspective is that of the three things to prioritize, progress, participation, and safety, it's kind of like you have those three and choose two. Unfortunately, it can kind of be like that, okay?
Yeah.
Like capitalism is really good at progress and participation, but it's not always so safe at times. Like maybe like a VC startup that is trying to just collect millions and billions of dollars, but doesn't have very much oversight of what they're doing from a safety perspective. But if you want something that's more, it's almost interesting. Of those three things, you can make like a Venn diagram. So capitalism is about progress and participation. Maybe authoritarian is about progress and safety, and then maybe something just more like stagnant is about safety and participation, where there's no progress. Yeah. So like being so regulated that innovation completely stops. Yeah. This initiative is trying to build institutions that balance all three goals, and basically we want to get on board with this, or what they're looking for is to share a project. I think okay, but what they're looking for is for people and groups who have an idea for some project or some like you need a concrete physical tangible project, or like a software sort of thing. Like it doesn't have to be like a really good hardware, but like you need something like a product that in some ways can help solve this trifecta triforce problem of some kind. Like maybe I don't know, like an online forum that's like a maybe like a social networking platform specifically for AI businesses or something like that. Maybe like some program, like a workshop, like a fellowship type program type thing. Like if we proposed a plan for that, we're able to get money to get that together of something of some kind. But once again, it looks like the deadline is. Let me just check. The deadline is When's the deadline?
July
Yeah,
11th, it looks like.
Did I say July?
Yeah, it says in the, yeah.
Okay, thanks. For some reason, a lot of things are due July 11th. I
Yeah.
don't know why. I have like 3 proposals due July 11th.
Wow.
And it's like I think that's when like the quarters for marketing.
Yeah.
But by the year, it's the end of the summer, like Q1, Q2. No, that's April, June. Maybe the next one starts July 11th. I don't remember. I don't remember the exact dates, but like it's like yeah. Okay, we can keep brainstorming. If you guys have ideas, if you guys have connections, if you guys have things that you yourselves, have been itching to find, like some intrusive obsessive thought inside your head that now has a source that you can fixate on.
Yeah.
Yeah. Go ahead and shoot them. We can keep chatting in the Slack channel or this
Yeah.
ideas. So at least from what I thought about from the first perspective. Okay, so some of the initial ideas that came to my mind was some sort of like a recommendation system for some sort of algorithmic based recommendation system for projects that can weigh different values and factors in a way that's much more balanced and effective. That's one thing that comes to my mind. Maybe like yeah. I don't know. If you guys have any ideas, I'd love to hear. So
Yeah, that'd be good. Yeah, we can do that in the Slack. Oh, Vidhi mentioned that. Yeah, she's our GSAC scholar for this year, and she's doing the open source sustainability. So, yeah, she just said that she had seen your project on the open source community sustainability. So she mentioned that in the chat.
but you mentioned weekly blogs you can share across.
Yeah.
Okay.
We'll put it in the Slack.
Yeah, I'm happy to talk more. Just all right. So CIP, the collective intelligence project that I've been talking about earlier. What are some good ideas to come forward with? And obviously, we're still in the brainstorming phase right now. But VR for EdTech being one of the biggest multi-trillion-dollar industries coming in the next couple of decades, that's easily one of the biggest things I look to right now, especially with my work for Alta Learning. That's the VR EdTech startup I've been working for the past 2 years now, and this is great for me to leverage my connections there with a CIP project for that stuff.
Yeah, that's good. So yeah, I wanted to talk about a few things before I'm gonna actually let Jesse do his thing soon, but I wanted to talk about a few things before then. So this is congratulations to Jesse Day. This is his graduation photo from UC San Diego. So he graduated with a master's degree in data science. And Hussain said congratulations. Vidhi said congratulations. So yeah, very good work, Jesse. Congratulations. And he has this red sneakers on there.
Yes.
Yeah. And then let's see. So this is something that, and this is following up, I guess, on a lot of things we were talking about with Morgan. This is a post from, I can't remember what blog this is, but this is Virtual Cells. So this is talking about virtual cells and kind of like, this is not science fiction. It's just kind of an informal discussion of synthetic biology and whole cell models. So this is kind of going from Hodgkin-Huxley, which of course was a model of ion channels in cells, to modeling entire cells where we can model every component of a cell and make predictions. So there's this quote in this post I like here. All models are wrong, but some are alive, which is nice. Actually, I can go to the homepage of this. This is udara.io, so this is where this is coming from. And they talk about digital twins of biological cells, often referred to as virtual cells or whole cell models, aim to recreate every relevant molecular process of a living cell in silico. This interdisciplinary endeavor marries systems biology, computational modeling, high performance computing, and increasingly AI. So the Hodgkin-Huxley model, of course, was a mathematical endeavor looking at voltage traces in the 1950s on an oscilloscope and then making out a mathematical model that fit those observations. They're not just descriptive, but they're also predictive. And so then that's the idea that we wanted to be able to simulate cells, but we couldn't because our computers weren't fast enough. So we relied upon Hodgkin-Huxley equations, which are actually quite useful in biophysics for predicting the behavior of neurons and other types of cells, electrical activity. But the idea would be that we could eventually build living systems entirely from code or some sort of mathematical model. And so in the late 1990s, however, there were a number of projects that started that tried to do this, tried to reach this goal. So there was a group of Japanese researchers then that worked on this hypothetical bacterium, and this was kind of happening at the same time that whole genomes of bacterium were being sequenced. So we were getting to an understanding of the whole genomes of bacteria, but more specifically the minimal genomes of bacteria, where you knock out all non-essential genes and you just have that set of genes that are required for minimal metabolism. So this was something that we could both sort of empirically look at and model with a computer. And so in the late 1990s, this group was able to reduce the genome to 127 genes and built the first prototype of something they called e-cell. So this was something that was a computer simulation. It wasn't very good, but it had some value because of what would come next. And so this virtual bacterium was able to simulate the expression of these genes in terms of a cell that's dividing and reproducing and living. And once we had this kind of a model, this would become sort of a basis for later experiments in synthetic biology. So this e-cell was more of a proof of concept than a practical tool, but it was sort of a sketch of what was possible. And so it would take until 2012, where there were groups that actually were able to work with more than just a hypothetical organism. And this is Mycoplasma genitalium, which is the simplest known free-living bacterium, where they were able actually to model then that cell. And so this is a group here that started working with this. What made this revolutionary was that this group immediately began breaking their virtual cell, deleting genes one by one to see what would happen. This is what I talked about when I talked about the minimal genome. Certain deletions could kill the simulation, but left real bacteria unharmed. And so now we know kind of what the essential genes are in a genome and how to model that, and how to get some sort of functional prediction out of what is basically a genotype and a phenotype. And so when you're working with bacterium, the phenotype is minimal. It's mostly driven by the genotype, but of course in more complex organisms that's not true, but we have to start somewhere, and this is why we're kind of focused on bacterium. And so what they're doing here is they're trying to build like one function into this minimal genome and see what could happen. So that's what they were doing here. And so then in 2016, J. Greg Venter's team at the J. Craig Venter Institute developed JCVI Syn 3.0, which was a synthetic organism stripped down to just 473 genes. This is, of course, this minimal genome, and it's defined as the bare minimum needed for autonomous life. So again, these are bacterial cells. These are bacterial genomes, which are basically just have coding regions with a little bit of a regulatory region in front of it. And so you can, there isn't a lot of junk DNA. There isn't a lot of stuff that we don't know what it does. So you can basically knock out most of the genome except for these genes and have a functioning cell. And so that's what they did here. And what the idea is, you basically reduce it to its minimal metabolism. And then you can add in genes to that genome so that it can do specific functions. And so it's kind of like the Anthrobots, where you want to strip it down to its minimal components, and then you want to add in things that add in directed function. So we know, like if you want to build a bacterium that digests some chemical in the environment, you can add in genes that specialize the bacteria for that. And you don't have to worry about, anything else, it doing anything else other than metabolism and the thing you specified for. So that's the idea here. And so but then they went a step further and they built a complete computational model of the bacterium. So this is where they've not only figured out this this minimal genome, but then they built a computational model of the genome. Okay, so then you have these whole cell modeling groups where they're pushing the boundaries of complexity in the opposite direction. Instead of minimal cells, they tackle organisms like E. coli with thousands of genes orchestrating the intricate dance of metabolism, DNA replication, and cell division. So you have to model a cell, you need to model metabolism, but you also need to model DNA replication, the rate of DNA replication, because that's important for understanding gene expression and later protein production, and also kind of things like what ribosomes are doing, what their rate of activity is. And then, of course, cell division, where cells divide and the population divides a number of times, and understanding all of that. So these models captured not just individual cells, but entire bacterial colonies, revealing how microscopic decisions by single cells ripple through populations in ways no biologists had predicted. So watching these simulations was like observing digital evolution and fast forward, mutation, selection, adaptation, all the forces that shape life on Earth, now playing out inside of computers. And then the next 3 years brought the infrastructure and validation that would finally move virtual cells from academic curiosities to clinical tools. And so in 2022, the FDA's CEPA initiative accepted computational human heart cell models as valid supplements to traditional drug safety testing, the first regulatory blessing for virtual cell predictions. And then Stanford's Vivarium platform launched, providing the collaborative software infrastructure that multiple research groups had been desperately needing. And so, but then of course we have AI in the mix, and now, we're able to bring GPUs to virtual cell development, and how we can use machine learning to handle all the complex gene expression patterns and kind of figure out what those might mean. So this person also gives a timeline going from 1952, the Hodgkin-Huxley model, skipping to 1999, which is Masaru Tomida's eCell platform, then to 2003, where you have these genome-scale metabolic models, 2005, the Blue Brain Project, 2007, the Blue Brain Project simulates the first biologically detailed neocortical column. In 2012 is the mycoplasma genitalium work. 2015 is the Human Whole Cell Modeling Project. 2016 is the JCVI SIN 3.0, and that was first released. And then 2016 is also the time of the Human Cell Atlas Consortium. 2020 is the major scaling breakthroughs in E. coli and S. cerevisiae. So these are just kind of larger bacterial genomes that allowed us to do this whole cell modeling. In 2021, we have JCVI SIN 3A, which is this whole cell model that was published. And this has like all the genes, 493 genes and their interactions of that minimal genome in the minimal living cell. Then the Vivarium platform in 2022. In 2022, we also get the FDA SEPA initiative. In 2023, colony level whole cell modeling. In 2024, the AI virtual cell roadmap. There's obviously a bias towards the most recent stuff being most important. In 2024, the Human Cell Atlas first draft. And we're at 2025 now. So this is, I think, a nice little overview of that history. It's a little incomplete because there are other things that were happening there that would fill in the gaps. But it just shows that progression from sort of simple mathematical modeling from like biophysics to these kind of whole cell models. So thank you. I think that was Morgan who posted that in the Slack. Okay. So now, Jesse, are you ready to give your updates and talk about the things you teased yesterday?
Oh yeah. I think you can hear me.
Yeah.
I'm a little bit. I'll go over the article. There's a few other things. Actually, might. Did I put it in here? Oh. I'm actually able to go to this today. I put in chat just an echo. I'll go through this briefly. It's part of the Echolopto stuff. I don't know how much Echolopto things have been talked about here recently. In terms of, I know Morgan's been to a couple things, and then the things even that I haven't been able to attend. I think there was one during my graduation last Friday that I tried to get into, but someone was mentioning like, "Oh, they're talking about cybernetics. You're going to want to be there for that." And so I guess I appreciate that I'm associated with that term somewhat, but I haven't been able to attend a lot recently because I've been all over the place. This one is later today, pretty close by, so I might try to go there. It was pretty last minute, so I think it's kind of just a continuation from. I know Addie, the director of Echolopto is in town, and I guess William Hahn is too. So I think they're visiting the area and hosted something at Augmentation Lab or something like that. So yeah, I'll check that out. I'll go through the little article that I posted. It was basically, it's kind of in the professional development realm and in the sense of brief commentary that just came up from a bunch of discussion. I won't go through the entire article. What I'll do is basically show out the, I'll go over sort of the context and the background for it. And it's sort of the foundation for some of the work that I'm doing regarding some other, regarding some other things I'm doing from here to there and some, kind of leadership or like eventual training and curriculum things that I want to do. But this is essentially, about, essentially this comes from having a lot of different conversations about I've had many conversations over the last week with folks from very high levels in very big organizations, including like some governmental stuff and also some a couple like startup type folks as well as founders and things like that. It's the same problem everywhere, and I find it to be particularly relevant to people that are trying to innovate or do new things, and that's sort of my general approach. But then specifically in terms of making, one of the people in the clunkier, bigger, bureaucratic organizations, even though they're in a much more bureaucratic type environment, they relate this extremely familiar pattern to everything that I've been exposed to already, and things that other people relate to. And it's funny how, regardless, it really is domain agnostic to me, and it's not. I say this post with the full. I guess I don't say it explicitly in the post, but the other side of the coin is like it's really hard. Like why is it why do deciders not decide? And what it's because it's hard. Like there's no two ways around it when you're dealing with essentially but in one sense you're dealing with a potentially unlimited number of options, and then you have to choose from that and be oriented towards specific outcomes. That's hard to do. It's a big risk. That's why it's why there's difficulty about it. But while acknowledging that, this post is sort of a critique or the start of a conversation about what the real role of I'm saying a CEO is here, but I don't really care about the title as much as decision making. I even reference in this slightly hopefully humorous way the decider of the George W. Bush area. So sort of a soundbite and a meme at the time. But I do think there needs to be essentially really clear decision making structure, or a chief decision maker, or a chief decider, whatever you want to call it. And I break it down into very, very broad categories of like, what are these decisions we're talking about? And to zoom out and give a little more context for those who are like just coming to the conversation or don't really know what I'm getting at, if you haven't been around either startups or people making choices at the top of an organization, and I'm being hierarchical here, mostly on purpose, but whatever it is the actual executive, I would say functioning, both ironically or like plainly, but the things that are deciding what at a high scale is done and the order to do it, and then transitioning between these states of development, like sort of like computational as in state change, at this sort of macro level, right? And it's part of what I want to develop in a lot of the work that I'm doing eventually is sort of this literacy of dealing with, it's almost like organizational literacy in and of itself, because I find a lot of folks come to this, usually your exposure to this is often downstream of it, unless you are running an organization or in the C-suite or directing a thing, or sort of directly at the behest of executive top level leadership decisions yourself, or on the business end of them, your exposure may be quite distorted. And I think, or if not distorted, your exposure may be indirect. So I'm kind of trying to bridge the gap and offer some language models, artifacts to understand what is happening. And I get towards the bottom of the post, I say like, when things don't go well, like this is what happens, and you may be feeling this in part of it. I've talked about momentum a lot in different parts in recent things. I've talked about it. I think this link will take us to. I think that's not the right link. I have to change that link. Yeah, this is another one here, but there should be another one here. Yeah, like this one. this is the momentum post that we've been referencing a lot, and it talks a lot about, you know, maintaining momentum and what happens if you do and you don't, and all this stuff like that. I'm not going to go to that now. But essentially, a lot of times people feel these pressures of things happening around their organization, and they don't know what it is. This is like the negative, you know, over time downside of things, and it gets worse and worse and worse. But there's all these, you know, there's, as you kind of get towards here, there's sort of, as you cross the border into like 4 and 5, there's sort of this negative infighting, lack of decision. People want to go and go and do something, do things that matter. And when we're not having decisions being made that aren't contextualized or actually being made, or that they're enduring, you kind of you incentivize this stuff. I continue to see the role of the decider as essentially, you know, you have to manage expectations and give people a sense of, hey, you know, it maybe doesn't have to be, here's the set list that I'm going to play, so you all know what tune to dance to for the next 2 hours. It doesn't be that prescriptive in one sense, but there's an element of like, you have to understand that the relationship between the investment of the people you're trying to lead or go on a journey with versus their buy-in and ability to do it. But there's a lot of trust, a lot of experience. You can be more quote unquote agile, maybe not the agile that we're used to, but like you can have flexibility and change with that. But when you're kind of at a base level or building something, if you're not making things that are contextualized in both the past and the present, and if you're not making a decision and understanding that there's a selection involved, understanding that one choice there's opportunity cost. And I think for people that are doing startups, innovation, creative work, that's really hard to deal with. And how do you communicate to people that have really cared about your stuff? It's like, hey, this was a really fantastic idea, we're not going to do it, you know. And how do you handle that? Do you have like bedside manner? Do you know, are these different pressures on who you communicate that to, and what does it look like, and all everything else, you know? And it's a very tough situation. But the goal of this post is essentially bring up this topic for discussion, because if you don't know that this is part of what's going on, it might make things challenging. You know, there might be a lot of lack of clarity or understanding about not just like the wheels of power that are at play, but more the sense of what is going on, and why are the decisions coming out the way that they do, you know. And depending on where you are in the organization, you won't have access to all the information or you won't have access to all the factors or influences or constraints or pressures that are at hand. But my advice, you know, which I talk about elsewhere, or like that I'm building some things around, you know, like my advice to you is generally to understand what these pressures are, so you can understand what is affecting the decision making process, you know. But at a kind of ideal level, which I talk about here, you know, what the chief deciders must do is choose, like make the choices. Or if you're delegating it, this is kind of a side story. If you're going to delegate to somebody, hey, you know, Jesse, okay, great, you're in charge of this. This is your thing. You know, you go do it. You have to allow ownership and authority, in that a lot of times, more often than I think people might ever even possibly fathom, the act of someone who is in a formal role or has the experience of whatever kind of authority says to somebody, hey, this is your thing, go do it. Now you are the decider here. And then it's sort of walked back, right? There's a incomplete authorization of decision-making or executive power or ability. And that's very, 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 very confusing to people. And I was in a conversation a few days ago where it's like, yeah, I had this idea, we were in agreement, we were agreeing, and then like a few weeks later, it was like, oh, nope, now it's actually, sorry, you can't implement any of your ideas, we have to just do like we did it before. And here's why, because it worked really well for me, and I know it works well this way, the other executive or person with the authority is like saying, oh, actually, no, we're going to do it this way. And it's just understanding that, one, part of it's sort of organizational therapy, my organizational clinical therapist hat, which I am not, so disclaimer. But if I was to do it, it's like saying, yes, you're right if you feel resentment in this situation. The feelings are valid because people are trying to invest and do things and make ownership and care about the project and really problem solve the project. But then you get pulled back on it, and it's very strange. And then another sort of side component to this is when you are given the means to, well, I don't know, if I'll close with the following remark about these things, and the following remark is, which I didn't. It's kind of what I'm going to focus on in a bit of the next post. Is basically, it is so important to understand that the real work of someone making decisions is to make them as best as you can, knowing that they're going to change, knowing things are imperfect, knowing that you may have to go back and forth on it. And it's tough depending on where you are relative to the projects that have to do. When people are investing in the project and you come a couple weeks later and say, hey, guess what? We're changing direction on this. Some of that's inevitable. But a lot of the hard work is communicating those changes when they do happen, so people can realize there's a legitimate reason to change them. But that's very different from what really compels a lot of the negative things to accrue over time here is when the decision makers are just not actually they're not. I know it seems kind of awkward to put here like it is, when they're not making the decision, when the decision is not chosen, because unless you're really focusing on what this is, it's from the decision maker's perspective, it's like, okay, well, I just have to decide this thing and be quick. I know I have to think about it and I'll do it. But what gets lost here is you're making people have to basically be contingent until you decide. And when they're having to be contingent or be hesitant, as you get toward like more and more and more of the culture shifting towards, okay, we don't have the action bias. And it was kind of funny, like, especially organizations like, or like the startups or these groups, like, yeah, we have a strong bias for action, so we're going to do things. And it's like, well, then you better have a really high functioning decision-making process. Because as I continue to go, and why I wrote the title of my role of decision makers, how I understand it is totally different than it was a long time ago, and even continued to evolve a lot in the last few years, is you have to allow people to maintain the momentum of what it is that you're trying to build. The creative process itself is very difficult, especially for those kind of things that in the spaces that I'm interested in a lot, like in the innovation space, people trying to build new things, people trying to make things in the world. So when you burden a lot of the creative efforts with these decision things, and it's inevitable to some extent, but the more you can let the creative process just be creative and not keep changing the structure, it's like if you have a stable developmental process for the young thing that's just developing and getting fragile. If you keep changing the environment, it's risky and it's harder to do, and then it may not, it may be failing to launch about it. So basically, the point of this whole I don't even want to call it an essay. It's more of an extended like note and feeling captured after the thing, and I want to do more with it ahead and building out some actual resources around this is for leadership. It's being really being aware that the quality and the timing of your decisions in terms of how they're able to be built upon, if they're durable, and if you allow this ownership and then you take the stewardship of it all and you're very real about it and you have sobriety about how the choices affected your leadership capital. Like, what did the choice, are others rewarded more easily because of the choice that you've made for their investment and efforts or not? And you have to sort of maintain that kind of earnesty, otherwise people aren't gonna buy in. And I think that's one of the things, particularly in innovation spaces, that is difficult to talk about, because when you're really innovating stuff and trying to build very, very new things, there's sort of a collective effort of creation and newness. So we're all kind of getting vulnerable about this together because we're trying to do something that we don't know. We don't 100% know yet how to do something. And so when you're communicating across those lines, it can be different. And when you're in a leadership role of, sometimes a leader or a CEO or someone founding a company might be a lot more comfortable in the creative space. Oh, I just want to work on the code. I want to work on the product design, and that's fine. That's why I say here, like, do you need to be the chief decision maker yourself for your startup or for whatever your venture is or your project to do well? Not necessarily. You better be on pretty good terms with someone if you do. But I think it's important to realize, like, I didn't have a conversation with this person, but there's this wonderful video of someone who has been running their company for, I don't know, 5 or 7 years, and they're like, you know what? I'm finally paying someone else to do essentially the chief executive type stuff, so that she could focus on connection, vision, specific development, like things that were more her natural strength. So this isn't a sense that everybody needs to be one size fits all and do this work. It's more really, really separating this out from the actual creative work and from everything else. Because if you have people waiting around for really important decisions to be made, kind of like the first person I said earlier, like they had a bunch of great ideas about the bigger bureaucratic thing to do in that organization. But if you have people waiting around trying to do it, then they kind of get frustrated. eventually they start thinking, well, what else can I do? And should I be here? Like, am I going to be able to trust this? And then if you keep waiting around long enough, it doesn't go well. So it's really realizing at a high level, and I'll close on this, but at a very high level, if you're in the role of a decision maker, there's a specific set of things you really have to focus on when you're doing the art of deciding. I think we don't. I've never really received any particular training. I've done a lot of things in the business world around this, and I've read books, but like the art of actually deciding is a little bit, I think, more esoteric than it should be. And then from the sort of the mid level or like people just joining the team or working in a group, like, yeah, like when you're evaluating a company and what you should do with them, it's really hard to tell from afar unless you have really great intel inside of how a group is working. But as you're getting to know them and thinking, how much do I want to invest in my time? Do I want to stay in this, company or group, pursue this with them? These are really important lenses to consider because um, as you can have a lot of great things, great people, opportunities, and great funding, but if you don't have decision making that's sort of aware of the innovation process itself, it can be challenging, and the challenges and the consequences you face and the things you feel in that process, may be a little bit underexplained, but they're valid too. So I will leave it at that. If there's any questions, we can discuss it. But I know it's a little later in the day too. So, what would you like to talk about now?
Yeah, that was great. So, some people, I mean, a lot of the things you talked about are interesting. We don't, we kind of think of decision making as like sometimes a very top down process where you're like, as a manager, there are people underneath, and then kind of tell me what to do. And then when we get into distributed decision making, it's often, we always think of that as maybe like uncoordinated or chaotic. But actually, that's not necessarily true because we can have micromanagers, which is make every, decide, make, decision making is basically every facet of the organization. But there's a line of thinking that says, basically that's micromanagement is poor leadership or poor decision making because you're trying to control things that you don't have a process for. And you're just trying to, react to that.
Mm-hmm.
And so, that I think really the sort of the hierarchical nature of the organization plays a role in that because you have like, you can have these highly distributed groups. Sometimes they're pretty good at what they do. They're more or less seamless versus organizations that are hierarchical but very dysfunctional. And so, I'm just thinking out loud here, but I think that's an interesting aspect of it that, decision making is, people kind of think of it as, there's always someone to kind of be held, to hold things accountable or to be held accountable. But in reality, it's like finding that person, there's a specific skill set, and it doesn't really, there's no one organizational structure that is foolproof there.
No, absolutely not. And it's really like my perspective changes on it too the more that I've been in the role of sort of the founder, co-founder too.
Yeah.
Because when you're trying to, it's a lot like when we were talking about like the Habermas machine stuff and the sort of mechanistic discussions recently in like AI governance and things like that. It's so much, there's not a one size fits all or best approach mechanistically, but it's sort of how do you, if you are building the very core or structure of an organization or a group, how do you create some kind of a functional structure for people to kind of, you have your sort of your core, and then you have like your intermediaries and your external collaborators coming through it, whatever shape it takes, whatever hierarchy it has. But there has to be some kind of clarity around, what is the mechanism you're implementing and buying in, asking others to buy into for decision making, conflict resolution, priority selection, right? And like this is really sort of theoretical, high level stuff, but it changes when you do that, and a lot of things that, because when you're younger or less experienced about some of it at an earlier developmental stage of your organizational literacy, if you will, when you're different, when you don't have the experience, you're often hit. You can be blindsided very easily, and anybody can be blindsided at any time about this stuff. But you can take a lot of hits or just be confused as to why the decisions happen the way that they did. And as you kind of grow in this literacy, and maybe, if you ever become a creator and not just a consumer of organization decisions, your ability to interface with them changes. And ideally, you know, you can get to a place where it's a bit like the idea of having, you can be a leadership at any position or have leadership at any position, and that's all cool and stuff like that. But what does that really mean organizationally is a bit like, what is the actual structure that exists? How are decisions being made? And what's basically the best way to dance to the tune or not? How do you work with it? And how do you understand what it is? And if you're, I'm not, I'm saying this post, I'm trying to ride the line between the generic criticism of executive functioning and executive decision making at an organization, and also bringing sympathy to the situation. But you know, it is a very challenging thing to do, to maintain a decision making structure, bring people into it, and have effective decisions. But I think it's just really important to say, hey, we're doing as best we can here, kind of presenting your due diligence that you're modeling the decision making process. You are modeling responsible decision making as best as you can, and then saying, I have my decision. I have the CEO hat on right now. I have the C-suite hat on. Whatever the top level executive thing, I'm going to do this. So have trust in me as I try to manage this decision making process as best as possible. So that way you or us doing the creative work can actually churn it out and buy in and trust that it's going to happen, because that's like the rub. That's the space where a lot of things do or do not happen. So that's my soapbox about that today.
Great. Thank you. All right. So yeah, thank you, Jesse, once again. So to finish up, I'd like to talk about this interesting group of papers or ideas that came out recently. It's a paper in Neuron, and then a response to the paper in Neuron, and then kind of where that comes from in I guess it's neuroscience and psychophysics. So this is a perspective article in Neuron, which usually means it's like an opinion piece, more or less. This is Jiu Zheng and Marcus Meister. They're at Caltech, and the title of this perspective is The Unbearable Slowness of Being. Why do we live at 10 bits per second? And so the idea is that, kind of considering the sensory speed at which we process the world. So we've actually talked about this a number of times in the group. We published a paper at Bika about this sort of problem where you're comparing two different species. You're comparing humans and insects, and how insects have a much faster visual processing system than humans, and making those comparisons in systems. So this is focusing on human cognition and sort of the bottleneck that visual perception in particular plays, but any sensory system. So if you think about your sensory systems, it's a bunch of sensory cells. They're picking up a signal from the environment. And depending on how they're arrayed, it presents this fundamental bottleneck for cognition. Now the question is you, of course, like let's take the eye for example. You're pulling in information from the world through the sensory system. You have these sensors arrayed in parallel. That signal is going into your brain and being processed. You can only take in so much information at one time. There's spatial limitations. There's a speed limitation. Some of that is biophysical. Some of that is, most of it's biophysical, but some of it is sort of the way in which things move wiring-wise from your retina to your brain. And so that's kind of the idea, is that there's this bottleneck. And so why is it there? And, what the consequences are. It's a very interesting question. It's always kind of fascinated me. So the information throughput of a human being is about 10 bits per second, as they say. I don't know where they're getting the number necessarily, but it's an estimate, and we can make estimates about that and compare it with other species or with other types of systems, and then make statements about what that means for sort of a sensory world or informational world. So you can think about like an AI system or a large language model. What is its sampling rate of the world? What does that mean for information processing? That sort of thing. Okay, so in comparison, our sensory systems gather data at around 10 to the 9 bits per second. So there's a difference between the information throughput and the sensory system's ability to gather data. And indeed, if you go back to the visual system, you know that there are a lot of sensory cells arrayed in parallel. And a lot of times it's gathering information that the cognitive system does not use. Or some of that information is redundant so that you have things, there's sort of a verification step, there's filtering of noise, things like that. And that happens before cognition occurs. So if you go to the computational neuroscience literature, there's a lot of stuff on this, this visual system filtering. And so, and the same thing happens in other systems in like sensory motor systems, the spinal cord and things like that. So we gather a lot of data at a much higher rate than we use in cognition. And as a consequence of that, our cognition is limited. And so the stark contrast between these numbers remains unexplained and touches on fundamental aspects of brain function. And that is, what neural substrate sets the speed limit on the pace of our existence? So why is it that we filter out so much information and end up with 10 bits per second? And we can ask that question as a function of cognition or as a function of biophysics, or both. Why does the brain need billions of neurons to process 10 bits per second? And again, that's an estimate that's kind of borne out by psychophysics. But it's interesting that, you have a lot more, seemingly a lot more neural hardware than we maybe need for what we're doing. Why can we only think about one thing at a time? Which is, of course, a classic result of experimental psychology, cognitive psychology, where you ask people to think about 2 things or 3 things at once, and it's usually a limitation of attention and a limitation of kind of thinking about keeping 2 things in your head at the same time. You can't necessarily do that optimally. You either focus on one thing and then move to another thing, or you kind of lose details of one thing as you fill in the details of another thing. The brain seems to operate in 2 distinct modes. The first is the outer brain, which handles fast, high-dimensional sensory motor signals, whereas the inner brain processes the reduced few bits needed to control behavior. So this is where the outer brain is handling this high-dimensional sensory, these motor signals, and then the inner brain is actually filtering this, or it's filtered down between the outer brain and the inner brain, and then it has relevance to controlling behavior. So this is, kind of thinking about cybernetics and the Evergood regulator theorem. So, we have a lot of input from systems, but we don't use all of that information to actually regulate things. And so that would be an interesting connection there. Plausible explanations exist for the large neuron numbers in the outer brain, but not for the inner brain. We propose new research directions to remedy this. Okay, so this is the paper here. They talk about, they sort of set this up as a problem of information theory, distinguishing signal from noise. So noise being all that capacity that we actually acquire, and then the signal is the distilled information that is post-constraint. So it says they give some numbers here. So they have this hypothetical game of 20 questions, where if the questions are properly designed, each will reveal one bit of information about the mystery thing. If the guesser wins routinely, this suggests that the thinker can access about 2 to the 20th, or around 1 million possible items in the few seconds allotted. Therefore, the speed of thinking, with no constraints imposed, corresponds to 20 bits of information over a few seconds, a rate of 10 bits per second or less. So that's their thought experiment where they're getting that number. More generally, the information throughput of human behavior is about 10 bits per second. We review measurements spanning the better part of a century that involve all aspects of human cognition, perception, action, or, as the example above, imagination. So they have this actually, they also get this from the literature on cognition, on perception and action. And then, of course, the signal and noises can be characterized using Shannon entropy and giving us this bit rate, or this bits per second. So, we're able to then use information theoretic approaches to compare the speed of processing across different mental tasks and processes between different neural structures in the same brain, across different species, and between brains and machines. So this is kind of what they're getting at here. And then this is where they talk about the information rate of human behavior. So they use English or language as an example. And they use this example of an advanced typist producing 120 words per minute. If each word is taken as 5 characters, this typing speed corresponds to 10 keystrokes a second. So how many bits of information does that represent? One is tempted to count the keys on the keyboard and take the logarithm to get the entropy per character. That is a huge overestimate. Imagine that after reading the start of this paragraph, you were asked what will be the next letter, and it says let, and it's like dots because we're trying to predict the next letter. English contains orderly internal structures that make the character stream highly predictable. So the entropy in natural language, or specifically the entropy of English, makes it easier to predict the next letter in a sequence of letters in a word. So you just don't have any letter that comes next. Typically, the language is structured so that there's certain letter combinations in words. There's certain orders of letters in words. And so we can calculate this using equation 1, and we can get a bit rate for that because, we have natural language and it's fitted to behavior, and it's based on taking in all this information about language and then crafting a language that's efficient for us to sort of produce as a behavioral output and process in our sensory system. Note that we have ignored any small variations in the way the keys are struck, and they get into this sort of model of thinking about how to generate natural language as from a human cognitive perspective. And so then this box 1 talks about measuring the information rate of human behavior. How rich is your behavior? Or to state it another way, how much uncertainty do I have about what you will do in the next second? So we can actually use Shannon entropy, which is equation 3. And this is where you have this, we take the probability of all actions as ith action, and then take a log transform of that, and then get a number that gives you sort of the diversity of different possible actions and their probability that it will happen next. And so they talk about this process, and then however that result is sensitive to how finely I measure your actions. So measuring the actions are important as well as the sort of the characterization of their possibility. As you scratch your toe, should I measure that movement in microns or centimeters? The finer I sample the movements to distinguish different actions, the larger the entropy according to equation 3 here. This is giving us this larger entropy. Therefore, what is a natural bin size for actions? And so this gives us this equation 4, which is I. This is basically sort of a conditional probability. So the presence of a concrete task leads to natural binning of the actions, in this case into keystrokes. It also allows us to separate the signal, namely the entropy that determines task performance, from noise, namely the part that does not. The difference between the total entropy and noise entropy is the mutual information, which is I here. So this is where you have two sources of information. They overlap in a Venn diagram. That overlap is a conditional probability A given C. So you have, the space of the overlap of these two sources of information as the source of your actionable information. And so then we also have this H A given C is the conditional entropy of your actions in the next second, given I know the entire context, which is here. And so this conditional probability is the probability that you perform an action in a given context C. And A times C is the joint set of all possible actions and contexts. So A and C have like these two different sort of actions and contexts, and then the overlap of those is your mutual information. And so in many examples discussed in the text, the task performance is considered perfect. For example, a manuscript without typos, or a perfectly solved Rubik's Cube. A performance without errors means that this mutual information equals 0, because the actions can be predicted perfectly from knowledge of the context. We adopt the use of information theoretic measures here because they allow a comparison of behavioral performance in neurons, networks, entire organisms, and machines using the same units. And so, these are all rough estimates. So it's interesting that they kind of give this framework. And this is not a new framework. They didn't invent this framework. This is actually, as we'll see, goes back quite a ways in cognitive science. So they give an estimate of the information rate of different human behaviors, including their time scale. And these are from different resources here. So binary digit memorization occurs at a time scale of 5 minutes and has an information rate at bits per second of 4.9 bits per second. Blindfolded speed cubing, which I guess is solving a Rubik's Cube, is at the time scale of 12.78 seconds and happens at an information rate of 11.8 bits per second. You have listening comprehension, which is minutes to hours. The information rate is up around 13 bits per second. Object recognition happens at 0.5 seconds, and the information rate is 30 to 50 bits per second. Let's see. Tetris operates on the time scale of minutes and operates at an information rate of about 7 bits per second. And then typing is minutes to hours and operates at an information rate of 10 bits per second. So this actually goes back to Claude Shannon and Kyle et al. So there are a lot of interesting research references in here. There's Hick and Hyman from the Hick-Hyman law. There's Fitz and Peterson from Fitz's law. And there's Shannon, who, of course, was the person who developed information theory in the first place. So there are a lot of references to different psychophysics laws and psychophysics researchers in this table. And they've all estimated these information rates for human behaviors. So they kind of go through this and they work out the math and some of the estimates. So it's a very provocative paper in that respect. Now there's some implications of this 10 bits per second limit. So one is forced to deal with the recognition that human perception, action, and cognition proceed at a glacially slow pace, despite the action in the world, despite maybe our ability to sense at a much higher rate. There's this limit to our cognition. This insight bears on a number of central problems in neuroscience, from learning and memory to the evolution of behavior to the design of neuroprosthesis or artificial intelligence. And so then, there's this question of how much information is stored in the human brain. We can calculate an upper bound on the brain's capacity by counting the number of synapses, which is roughly 10 to the 14th, and multiplying it by the dynamic range of synaptic strength, estimated at 5 bits. So this results in a capacity, if we multiply those out, to around 50 terabytes. And this is the amount of information required to specify all synapses. So that's, again, you can do these estimates in different ways. And so we basically can say there's an upper bound of about 50 terabytes. And that's probably an overestimate, but we can do that and then kind of work from there. So that's, this kind of business is interesting because you're kind of making these assumptions about human cognition. Some of them are measured through experiment, but a lot of them are kind of assumptions about the dynamics. This is talking about the speed of light for different species. So how can humans get away with just 10 bits per second? The answer here is that cognition at such a low rate is sufficient for survival. More precisely, our ancestors had chosen an ecological niche where the world is slow enough to make survival possible. In fact, the 10 bits per second are needed only in worst-case situations. Most of the time, our environment changes at a much slower pace. So this contributes to the common perception among teenagers that reality is broken, leading them to seek solace in fast-paced video games. Okay, the idea here is that you can have a slow world or a fast world. So, and it's dependent on your ecological niche. So for humans, our world is slow, whatever that means, and that there are differences in that. Maybe by development, maybe technology increases that, and so that's the world we live in. And then for snails and worms, their ecological niche results in a much slower world still. And then they say here, occasionally niches intersect with disastrous consequences, as when a snail crosses the highway. One may ask whether they're animals operating at much higher information rates. Candidates might be flying insects that perform acrobatics in turbulent airflow, or birds that navigate through tree clutter at high speeds. So yeah, they've actually done some pondering about this. I've done a couple blog posts on the speed of movement in different organisms, and it's really interesting. There really isn't a lot of work on it, so that might be something to follow up on, thinking about those kinds of problems. So let's go back to the let's see. So this article is pretty provocative. It gets into a lot more things here, and it really it's built on this background of psychophysics and using information theory to study cognition. Now, one of the papers they talk about is from Fitz, and there's this idea in motor control called Fitz-Law, which is where you might have a target of a certain size, and you have an operator that, they have an effector, which might be a hand, or it could be a robotic hand, and then a visual system that verifies kind of the movement of an object from one place to another. And the idea is that if you're like operating a robotic hand, or if you're operating your own hand, you pick up something from a table and you move it to a target and you place it on the target. And as that target increases in size, the task becomes easier. And as you restrict the target size, the task becomes harder. So it's like this, you're moving the pen from one part of the table to another. The pen is a certain size relative to the target. If the target is exactly the size of the pen, it's harder to make the movement and place it. If the target is the entire table, it's very easy to hit the target, and it's thus faster. So it's the speed of perception, the speed of behavioral output versus like the physical constraints. And so this paper here is the classic from 1954. This fits the information capacity of the human motor system in controlling the amplitude of movement. So this is from the Journal of Experimental Psychology. And so this is where they worked out this model for motor control and calculating this amplitude of movement, which is moving from some source to a target, and how fast that can be done. And that's a function of perception of the target size and estimation, but also the speed at which you can make that behavioral output from your, so information is coming from your eyes, it's being processed into that slower system, and then it's making the movement to the target, which is of course constrained by your muscles and your joints. And so that's all calculated as information theory. We don't consider all of the components of what's going on. We just have this very simple model of behavior. So that is the source of this, sort of the assumptions made in this paper. And I think it's pretty provocative in the sense it's not wrong, but it's kind of like, it's a bold sort of statement of how things stand. Now that brings me to the second paper, which is sort of a rebuttal to this, or a comment. And that is this paper, The Brain Works at More Than 10 Bits per Second. And it's sort of maybe like, okay, that's nice, but it's clearly not the whole story. So the abstract here is: a recent article makes a claim with far-reaching implications for neuroscience, technology, and society, that the human brain is subject to information processing speed limit of 10 bits per second. Okay. Although the speed limit appears to hold for high-level cognitive functions, like decision-making or maybe, motor control, we argue that unconscious processing for real-time control of movement, which occupies a majority of neurons in the central nervous system and accounts for most of the information throughput of humans, substantially exceeds this limit. And of course, this is not exactly anti this first paper's argument. It's just simply that you have to consider maybe that those massive neurons, that those unconscious processes play a larger role in sort of producing the output behavior than was assumed in the first paper. So they kind of get into talking about the control of movement in complex, unpredictable, and often dangerous environments is a vital function of the nervous system. Consider an experienced athlete running across a Rocky Mountain ridge. Every 250 milliseconds, they must swing the leg forward, ensuring their foot clears any protruding rocks, then place the foot on an appropriate support. This requires intense, active visual monitoring of the ground ahead. Because the head is subjected to random, broadband linear and angular motion, the nervous system must sense this motion and rapidly move the eyes to stabilize the scene on the retina. And so the athlete's nervous system has to use a host of sensory signals to do all these corrections. So the idea is that it's not that you're filtering out this extraneous information and not using it and then just focusing on that slower bandwidth or that lower bandwidth. You're actually using all this information, but it's not being translated into the main event of behavior. It's translated into this corrective behavior that we're not measuring in the case of, say, Fitts law. So A recent paper makes an astonishing claim. Although the brain collects a vast stream of sensory information, the information throughput of a human being is about 10 bits per second. The authors define throughput as the information shared by the environment and a subject's actions within a 1-second window of time. The throughput, in their view, encompasses all motor actions, as well as perceptual and cognitive processing. To compare the flow of sensory input entering the nervous system with throughput, the authors first estimate the maximal information rate at the first stage of visual processing in the retina. By carefully analyzing the dynamic range, noise and membrane potential, kinetics of photoreceptors, they find that sensory information enters the nervous system at a rate exceeding 1 gigabit per second, which is a huge difference from what we see them thinking is the sort of the relevant information for cognition. This sensory information flows through and is processed and filtered by immense distributed networks in the brain, resulting in the firing of motor neurons and other such things. Then the authors next determine the information throughput of a human, not by measuring the uncertainty and the rich signals leaving the nervous system, but rather by calculating the degree of randomness in sequences of abstract signals, such as letters or numerals, people produce in a range of tasks, such as typing, memorizing binary digits, solving Rubik's Cubes, reading, and speech. So this is where they get the 10 bits per second number. And so they then suggest the enormous ratio of sensory input to motor output, which they estimated approximately 10 to the 8th, and refer to that as the brain's sifting number. So this is not, this is where we take all of that diverse input and sift it down to like the essential stuff. So that's basically, and then they're criticizing that as being very simplistic. They're saying, you're just basically constructing this model from like just to fit maybe information theory as opposed to considering this from a broader perspective. As I'm reading this, I'm thinking that there's this kind of, maybe this rivalry in this particular question between dynamical systems theory and information theory. That is, information theory forces you to make this sort of assumption of sort of, finding the core sort of information of a task. And of course, if you go back to the the cognitive science literature, like the 50s and 60s, that was kind of what they were doing. People not only did that with movement behaviors, but they did it with other psychophysics, discovering objects in an array. And then, of course, there's the whole literature on working memory, is holding a certain number of bits in working memory. And so if you want to find out more about that, you can look into that. But basically, the idea is that human cognition operates as information processing. We can characterize information processing as this this bit rate, and that it's very much like a computer. It's processing discrete symbols, and it's moving along. And that's this is happening in sequential, as a sequential process, and we're not going to consider any sort of parallel processing or anything happening in the neurophysics, in the biophysics, in the neurophysiology. Now, kind of what they're arguing in this article, and they don't explicitly say it, is that there's this dynamical systems aspect, where at the very least, there isn't really the sifting. It's that the stuff that they're talking about in the first paper is this sort of maybe the most salient behaviors that you can measure, and then there are these other behaviors that are generated that they don't consider, and that all of that might be better described by a dynamical systems model. So for motor control, for example, we have dynamical systems model. A couple weeks ago, we talked about synergetics as a model for looking at dynamical systems in behavioral outputs. So, getting, like people do these postural sway paradigms where they have people stand on a force plate and they have them kind of look at a stimulus, and people shift their weight on their feet back and forth and around, and they produce this sort of trajectory that is characteristic of the influences of sensory inputs on their body. and you can measure that, and you can get a sense of whether they're healthy or whether they have some sort of movement disorder, or whether the cognitive sway can change with the sensory input. And so a lot of that information is going into corrective behaviors like that. And then maybe you perform another task where you solve a Rubik's Cube, and you can measure that, and you can measure the bit rate. And then, you might say, well, if they're spending their time solving the Rubik's Cube and they're paying attention to that, maybe their postural sway suffers. And maybe that's true, but it's more than likely you won't find a correlation between the two. So really a lot of this is based on the estimates that you use, the model of cognition that you use, the model that you use to analyze things, and your ideas about what constitutes behavior. So it's an interesting set of readings, interesting set of questions, and that's all I have for that. But the ongoing controversy, I guess, and it links into things, greater questions in cognitive science. All right, so I think that's it for today. A little bit longer than that, but that's okay. All right. Anything else before we go?
Yeah. Nice to see you guys again.
Yeah, nice to see you again.
This is great. I mean, even that work on the the nervous system kind of just being like, despite everything about technology, about our health and improving things, as humans, there are just some things that we're just naturally very bad at, like multitasking and things in general. And if information processing is so fast, why are we as people still so slow? I mean, I appreciate that, the paper that you were just going over there. I think it's interesting stuff. I think I just want to give you guys a brief update on the project I'm doing with Richard Gordon too.
Okay.
It's a shame he's not here. Do you know if he's just like busy today? I don't know. He's usually here, isn't he? I don't know.
No,
Maybe he's more. Oh, he's not. Okay, so he comes to the Monday meetings with. Okay, never mind. That's okay. But yeah, we are. I'm meeting with Dick and Mohammed Majid Al Rifai. He's one of Dr. Gordon's colleagues over at Greenwich, over in UK. We're still getting we're getting our research and reports and writing together for applying for grants for our project. Yeah.
Okay. Sounds good.
So
yeah.
It can be pretty slow because we're all balancing different stuff throughout our life. So
All right. That's all we have for today. I guess we can call it a day. Thanks for meeting.
Yeah, thanks.